elements that would be at that mass that should have those characteristics. So that was pretty cool. So now we have a more complete understanding of the periodic table. And the design of the periodic table is very useful in how the elements react, their characteristics, and how they will bond with other elements. So that's why the periodic table looks weird, right? It kind of looks like this castle. There are more elements in the first row and the second row than all of these guys. And then you have this weird, up there again, right? So there's none that are kind of up in this middle above the transition elements. So that's on purpose, and that's based on the characteristics of the elements in the table. So the elements are arranged in these families. And so families are the columns that are going down the periodic table, right? So here is the first family is the alkali metals, right? And they're all going down here. They include lithium, sodium, potassium, rubidium, cesium, and francium. Hydrogen is up there again, but we're going to ignore this one currently. It kind of has its own characteristics because it's so small. But all of these guys are really highly reactive. Has anybody seen like a reaction of sodium with water? What happens? A boom, yes, it explodes. So if you have pure sodium, elemental forms of sodium, if you throw them into water, they will explode because they react so violently with water, right? That is characteristic of this whole group. And the farther you go down in the table, the more reactive they are, right? And so you can see really explosive reactions. If you hop onto YouTube and look up cesium in water or sodium in water, you can see people who have done that. All right, so the second family is the alkaline earth metals. These guys start with beryllium and come down, and all of these are still quite reactive, but not as reactive as the alkali metals. A little bit less reactive, but still pretty highly reactive. The elements that are all shown in purple here are called transition metals. And we'll talk about some of the features of the transition metals, but you won't have to know those as well. But you do notice they're all in this place. And then coming over here, we're kind of going to ignore these guys and jump over here to the halogens and the noble gases. So you'll need to know this family and this family as well. So you've got 4 families to learn. The first 2 and the last 2, right? So this last one, the halogens, start with fluorine and go down to iodine, and then the noble gases on the very end. So fluorine is the most electronegative element, means it really wants to attract an electron, and we'll talk about why that is. But all of those elements in the halogen row, they really want one more electron to make them look like a noble gas. The noble gases, on the other hand, are all full, and they're very non-reactive elements. They're typically gases as well. All right, so let's take a look at our atomic structure, and then we can overlay this on the periodic table and see why those elements are lined up in their family groups the way they are. So atoms have 3 major components to them, and they contain a nucleus where 2 of the particles are going to be found, and then they contain an electron cloud where the electrons are going to be found. So inside the nucleus of the atom, the 2 particles that are in there are the protons and the neutrons. And so our protons are positively charged particles, and the neutrons are neutral. They do not contain an inherent charge to them, although they're made up of charged particles. So the more we learn, the crazier the world gets. But they balance each other out, and so their overall charge is neutral. The electrons are floating around, spinning around the nucleus of the atom, and they move very quickly. They're very, very, very tiny in comparison to a proton or a neutron, and they take up most of the space of an atom. So if you're kind of thinking on a large scale, something you could think about, if you think about a baseball stadium, right? That's a very big place that can hold 70,000 people, something like that. Well, the atomic nuclei of an atom might be like sitting on the pitcher's mound. And then the rest of the space in the stadium would be where the electrons would float around the atom. So most of the space in the atom is the electron cloud, where the electrons are floating around. And then the atomic nuclei is just that very center space. All right. So our atomic structure, again, made up of these three major particles. The proton, the symbol is a P, and you have a plus superscript on there because it has a positive charge overall. And then the neutron is neutral, lowercase n with the superscript 0. And the electron, lowercase e, with the negative symbol as a superscript because it is negatively charged overall. So the relative charges of the electron to the proton are a -1 and a +1 charge. And then again, that neutron is neutral. So the charges of one electron and one proton will balance each other out and make a neutral position as long as you're 1 for 1, right? So even though there's a huge size difference, right? So you can see if we have relative mass of our protons to electrons, right? The neutron's about the size of a proton. They're about 1 to 1. But the electron is 0.00055 compared to a proton, right? And if you look at the mass, I don't know why we use kilograms here, that's a huge number. But you can see the electron is 9.1 times 10 to the minus 31, whereas you've got orders of magnitude higher for both the proton and the neutron. So electrons are so small that they don't really even contribute to the mass of the atom, and we ignore them when we look at the mass of the atom. All right, so the electrons don't circle like an orbit. Like when we throw up a satellite around the Earth, it's orbiting around in a nice circular orbit around our planet. The electrons don't do that. The electrons, we can predict kind of where they'll be, but they can move in like dumbbell shapes and kind of weird shapes around the nucleus of the atom. So we tend to say that they are in an electron cloud, and they're somewhere in there. So the minute we predict where they would be, they've moved, and now they're not there anymore. So it's only a predictive tool that we have for electron movement. All right, so there is this thing, though, where they're layered into different shells, right? So as you're expanding out from the nucleus of the atom, we can build a model of where specific electrons will be found. And the closest shell into the nucleus of the atom can only hold 2 electrons. And then that shell is going to be full after 2. And then each subsequent shell can hold more and more electrons because the shells get bigger as you go out farther away from the nucleus, right? So this second shell can hold 8, and then every outer shell can hold a maximum of 8 electrons in the very outer shell. Yes. Okay, so this gives us the octet rule. Right? So the maximum number of valence electrons within an atom is going to be 8. And this is going to be very helpful for us to predict how atoms are going to interact with each other and how they're going to bond. So they're essentially full when they have 8, right? And not full if they have less than 8, right? Okay. The exception, again, is going to be hydrogen and helium because they are so small. Hydrogen and helium only have this first shell, so they are full at 2, right? So hydrogen will have 1 electron, and helium is full, has both electrons, and then they are full. So that's why they're kind of strange ones up on the periodic table. All right. So again, hydrogen only has that inner, right? So it has one electron, and then it's going to be full, right? If we're looking at our arrangement of our groups and our families, we can think about their position on the periodic table and their valence electrons, right? So hydrogen has one electron, and so does all of the other family members under it. Lithium, sodium, potassium, rubidium, cesium, and francium have one electron in their valence shell, that outer shell, right? If you go to the alkaline earth metals, they all have two electrons in their valence shell. The elements have more electrons than that, but in their outer shell, in that valence shell, they only have two. All of the transition metals have two electrons in their valence shell. And then the main family groups, you start moving up at this position here, 3, 4, 5, 6, 7, and then the noble gases at 8. Okay, so this is the valence shell based on the family numbering of the main group elements as you go across. So they're placed into their families based on how many valence electrons that they hold, and then also their proton number as you're going across. That's going to become a major element to this as well. So let's do a little more practice. All right, so we got a little bit more detail for the families. Our green element, again, is magnesium. So what is this an example of? There, you can see our class name up there again, sorry. All right, we have all the answers. Best guesses? Very good. Magnesium is an alkaline earth metal. And this guy down here, iodine, which family group does that belong to? And we have all the responses. Best guesses? All right, so iodine is in the 7th family. That's our halogens. How many valence shell electrons does silicon have? Yeah, because it's useful to be able to say, oh, what is the group 11 transition metals? Yeah.
You know it's 2, no, it's 11.
So you can name them 1 through 18, or you can name them as their families. 1, 2, kind of ignore the transitions, 3, 4, 5, 6, 7, 8. Yeah. So the periodic table is, I don't know, like the chemist's Bible. Right? There's so much information in here, and there's different ways to talk about it.
Right.
Yeah. So if I'm talking about like the transition metal number 4 group, you could go there.
Too, 'cause you could just take off
Yeah.
like 13, you just don't look at the 1.
Yeah. Yes.
It's kind of off topic, but looking at the periodic table, on the right side of the 18 column, what are the teeny tiny numbers?
That's the position of the electrons in the electron shells around the nucleus of the atom. So that first shell, very small, can only hold 2. Right? The next shell out holds 8. The third shell out holds 8. But then you can see if you drop down to that 4th row, you've got 18 in the third around, and then 8 in the outer shell. So the outer shell can only ever hold 8. Right? But the inner shells can then hold more, right? And the inner shells can gain more after the outer shell fills up. It's a weird energy thing. I won't demand that you know the electron configurations, just the outer shell holding 8 so that you can do the bonding.
So I guess my question would be, so say there was like, what, 4 like valence shells, and it would go to 8. And could we have a 16, but then the last one would have to be 8? Or where would the 16?
The outer shell fills up before the inner shell. Yeah, so there's orbitals. I kind of think of them as like apartment buildings. The s orbitals hold 2. The p orbitals, there's 3 of them, and they can hold 2 each.
Yeah.
The d orbitals, there's 5 of them, and they can hold 2 each. So for the d orbitals, they can hold 10. And you'll notice walking across your transition metals, there's 10 transition metal rows, right? And so those fill the d orbitals as you go across. Yes, but they fill the inner shell versus the valence shell. The d orbitals are never in the valence shell. Yeah, so they have to fill after the valence shell fills up. The valence shell is only the s and the p orbitals of the outer shell. That kind of makes sense? Yeah, and then as you keep going down, you've got the f orbitals, and they will fill up with the lanthanides and actinides, but they're very big, so we don't go there. Yeah, but the periodic table, I don't know if we go back to the periodic table. Right? The lanthanides and the actinides are not like shown in the periodic table. They're like always underneath so that I can print the periodic table so you can see it. But they actually go into the periodic table here. So it's like you would split the periodic table and push everything over and add the lanthanide and actinide rows here. And they would go in the periodic table there. Yeah. Based on electron configurations. Okay, good, back to this one. All right, so silicon, when you're walking across the periodic table, you've got 1, 2, all the transition elements 2, the boron row 3, the carbon row 4. So silicon is below carbon, so it should have 4 valence shell electrons. Oh, we haven't done this yet. Let's stop there. Don't answer that one yet. All right, it's here. So there are 2 numbers. If you're looking at the periodic table, they don't necessarily have to be placed right in the placement of the upper left corner and the upper right corner, but they can be. So you've got 2 numbers that you need to look for. The first one is the atomic number. So the atomic number shown here, see where it's at on this periodic table, it is in the upper right corner of each element. is the atomic number. This is the number of protons inside the element, right? The proton number is critical for determining the element, right? So an element is determined by its proton number. All carbon atoms have 6 protons in them, right? If it has a different number of protons, it is a different element, right? So the element that has 7 protons is nitrogen. Only nitrogen has 7 protons. No other element has 7 protons only, right? So an element is determined by its number of protons, and this is called the atomic number, and it's given the letter Z. So your Z number is the number of protons, and that is the definition of that element. So your number of protons determines the element. The other component there is the atomic mass, or the A number. So atomic mass can be shown up in the right-hand corner, or it can be shown at the base here. When it's shown at the base, then your proton number is up at the top of the box. So when you're looking at this periodic table, right, you can see the mass numbers are below each element, right? And so the mass number is a contribution of both the protons and the neutrons. So I told you the relative mass of each of these guys, right, is 1, right? So you would think, well, how do you get that mass number that's in between? You can't have half a neutron or half a proton to give you that number. So I told you that the number of protons is fixed for each element. It defines the element. But they can have different numbers of neutrons, right? And so you can have different isotopes of the same element depending on how many neutrons that it has inside there. And so the atomic mass that's up here is the average of all of the isotopes that are on the Earth in their relative abundance. So our periodic table is very specific for the Earth. And it's really the surface of the Earth, not really the core of the Earth, what we can find out there. So if you went and scooped up a bunch of rock and then you isolated the copper in it, it would have a mass of about 63.55 when it's pure, right? Based on the composition of the copper that's in the Earth. Okay, so atomic number, Z, number of protons, fixed for the element. That defines your element. The atomic mass is a combination of protons and neutrons, and it is an average of the different isotopes that are present on the planet. All right, so defining isotopes a little bit better. Atoms of the same element, again, have the same number of protons, but they can have different numbers of neutrons. So hydrogen is a good example. It has 1 proton. So any atom that has 1 proton has to be hydrogen, right? But hydrogen can have no neutrons, right? And so this is the bulk of hydrogens out there are in this form, right? Hydrogen can also have 1 proton and 1 neutron. This one we call deuterium. It is a form of hydrogen. And then tritium is the other form of hydrogen. It has 1 proton and 2 neutrons. Tritium is the radioactive form of hydrogen, right? So the main form is this one. And I can tell that because my periodic table mass for hydrogen is 1.00795, right? That's almost just the mass of 1 proton. So the bulk of my hydrogen is in this form, right here, in the hydrogen form. Deuterium and tritium make up very, very small amounts on the Earth. But the tritium is radioactive form, and in chapter 3, we'll talk about what that means. But essentially, it's unstable. All right. So our isotopes can be written in this format here when we're talking about a single isotope of an element. We're going to write its atomic mass up on the top, right? And this is the neutrons and the protons. And then we'll write the number of protons in the lower part of the atom. This has to be fixed, right? So all copper atoms have 29 protons in them, but they can vary in the number of neutrons that they have, causing this number here to shift. But if I write it like this, I'm only talking about this single isotope. How many neutrons does this isotope have? Right, if we subtract off there, did I hear a 34? Yes, right? So if we take 5, 13, 4, 34 neutrons. All right, so if you add them together to get this number, you can subtract off the protons to get the number of neutrons. So if I write it like this, I'm referring to the copper that has 34 neutrons only, not any other isotope when I write it in its isotope forms. All right, so on the periodic table, this is a combination of the different isotopes of copper that make up its mass on the Earth. Right, same for the other elements as well. Okay, so this is how you would calculate this. And when we do our lab for week 3, you'll get more practice doing this. I know, it's like, oh my God, what is that? All right, so this is just taking percentages of the abundance, relative abundance on the Earth, and then breaking them down. So copper has 2 stable isotopes. The 63 copper, right? And so, whoop. Oh, no, go back. Sorry about that. All right. So the 63 copper, right, has 29 protons. And the 65 form also has 29 protons. That's a 9. All right. So our 63, if we are looking at the atomic mass, is 62.93, and it has 69%, roughly, of the copper found on Earth is in this isotopic form. So percentage, right, is out of 100. So we can write our percent like this, 69 out of 100, and we can multiply that. And then we can add it with its other form that's on the Earth, is the 65 form. The actual mass is 64.93 Daltons, and there's about 31% of it on the Earth, right? So we multiply it by 0.3085, add those together, and we get the atomic mass that's on the periodic table. All right, let's do a little bit more in our Socrative. So now we can take a look at atomic mass of an element is determined by the number of neutrons and protons present, while the number of electrons is not a factor since their mass is so small compared to the neutrons and protons. Is that statement true or false? Don't be scared. All right, we have all the responses. Best guesses? All right, so this statement is true. The atomic mass is determined only by the number of protons and neutrons that are in the atom. We ignore the electrons because it's so small, it would be like 0.000 off to the end, and it wouldn't change our number at all. Okay, protons carry a charge of -1, where electrons carry a charge of +1. True or false?
Don't mind me the whole day. Stupid. I'm like, yeah, I know that. How is it in person?
And do we have all the responses? Very good. That is false. Our electrons are negative. Protons are positively charged.
I was like really crying.
If an atom has an atomic mass of 195 and 78 protons, how many neutrons does it have?
That's what you put. Can't determine the it's like that. I'm like, I don't have an
Oh, I didn't have to. Like, look. One was 78. I still wanted to double check. Well, now it's neither goes.
And we have all the responses. You're all in there? Last chance? All right, so 117 is the correct response. So you can find the neutrons by subtracting the protons from the atomic mass. That should give you the number of neutrons. What element is this? Yeah, looking at the periodic table. PT. Some records may get this label. Platinum, yes. So it has to be that one, right? Because that's the only one that can have 78 protons, right? So you know the element based on the proton number. Oh, we didn't talk about the number of electrons, did we? All right, I have to let you cheat on this one. No. So elemental forms of atoms are neutral in their nature, right? So however many protons they have, that's how many electrons that they also have. So the proton number is also the electron number when you have an elemental form.
Also 65. Or no, 30.
That's the mass. So the proton number. Yep. What element is this one? Yeah, did I hear a vote for zinc? This one is zinc. So zinc has 30 protons, so it must have 30 electrons. All right. The uranium isotope 235 contains how many protons? Oh, we have to find uranium up here. Anybody see it? How many protons there are? 92. Yes, uranium down here. Uranium 235. How many neutrons would it contain if it has 92 protons? Cross off A. That's the number of protons, right? Oh, sorry. It would be. It would be A. I'm tricking you, aren't I? Yes, it's the number of protons, yes.
What is the 235 count? Sorry to ask, like, what is the 235?
That's the mass.
Mass, okay.
Yep, so if you subtract 235 and 92, you'll have the number of neutrons that are left. What is the average mass of uranium? Let me see over there. 238. So this form of uranium is much more rare, because the average mass of uranium is much higher. All right. You have all the answers. Whoops, I'm sorry. I didn't show you the result. It is 92, so you can always use your periodic table to find your number of protons, which you will have on the exam. Yep. We'll go back. Okay. Oh, yes. Gallium has two naturally occurring isotopes. The mass of gallium-69 is 68.9256 atomic mass units, and it has 60.108% abundance. The mass of gallium-71 is 70.9247 AMU, and it has 39.892% abundance. Calculate the atomic mass of gallium. So you want to set it up the way this problem is set up here. Right? So start with your atomic mass of the first one. Right? So we have gallium-69. The atomic mass is 68.9256 AMU. Right? And the percent abundance is 60.108. And that's out of 100%. Right? And then the second one is 70.9247. Right? And that one has 39.892% abundance. That's out of 100. And that should give you an answer. This is for gallium. How can you confirm your answer? Yeah, you're like, I'm not gonna look at the periodic table. Hopefully you get that number. Maybe? What if I said on Mars? Can you use our periodic table? No. Our periodic table is for the Earth. So be careful. I may trick you. And I'll be like, what is the elemental abundance on this asteroid? Yeah.
Honestly, it works better when you take the 60.035 by 100 times that. You can do it like that, right? You don't have to do it. You can take 60.108 divided by 100, get that number, times it by 68.9256. And then
Yes.
do the same thing on the other side there.
Yeah. You can just move these back too.
Yeah.
Get rid of the 100 altogether. Yeah. I just like to show where that number comes from, that it is the percentage out of 100. Yep. All right, we have all the responses. Very good. Oh, okay, we haven't done this yet. Got to stop there. All right. So I think now's a good time to take a break too. So let's come back about 3 after. If you are in the online lab and have not picked up measuring device for this week's lab, come up and check one out. Let me have you put your name right under here, and then I will check about kids. And you are?
Maybe next lab.
Are you on? Okay. Yeah, so last week's lab was just math review. So you can download the worksheet and complete it. And then upload it to the Canvas site, and then email me and let me know that you did that. I can send you the soccer tip from last week as well. You don't need this. Yes. No, it's not fine. You bet. Awesome. Good.
Yes, we're good. Yes. Yes. I'm gonna what's his birthday? I'm gonna do this.
No. It's on the 8th.
So why did you celebrate it early?
Because I got his thing even in the morning.
So you celebrated early?
Well, no, I'm gonna celebrate again. That was a pre-celebration. Yes, I got his thing in.
We got all of that.
Yeah.
So you're the 8th?
Yes.
Oh, today's only the 6th. Holy shucks.
I'm just a a really tricky thing when you look at an actual piece.
And do like a 10,000 word paragraph to go with the caption.
The socks.
There's socks.
I started the socks that you're supposed to wear their compression socks, so
What? So, you know this yoga pose?
All right, let's go ahead and start again. Before we get into moles, I just want to point out on your periodic tables, if I can draw you back in, if you're looking at the periodic table, right, if you're going across the periods, which are going across, you can see helium or hydrogen and helium are up on the top, and they're in the first period, and then you drop down to the next. That corresponds to that inner electron circle where the electrons can be the closest to the nucleus of the atom, and then it's full, right? So, and you can see up there, right, 1 and 2, that first period is full. It is the first electron shell. Then you go down to the second period. You start with lithium, beryllium, work across boron all the way to neon, right? That has two areas where electrons can exist. It has the s orbitals that house 2, and it has 3 p orbitals that can each house 2. So it can house a total of 8 in that outer electron shell. And so you see they go up in order: 3, 4, 5, 6, 7, 8, 9, 10. So as you move across the periodic table through each period, you are going to gain 1 proton as you move across. You also gain 1 electron as you move across because the proton number equals the electron number, right, as you go across, right? And your shell, where you can house those electrons, gets bigger as you go down on the periodic table. So that's one of the features of the periodic table and why you gap the transition elements in levels 2 and 3. There just are no transition elements up there because you don't have the space to house electrons in those orbitals at that level. You only have the valence electron shell. All right. Okay, so that's a periodic table. The next really, really cool thing about the periodic table is this concept of the mole. So you've already been introduced to the mole. You've been doing conversions with it, right? And we know that Avogadro's number is the mole number, right? Is 6.02 times 10 to the 23 atoms or molecules makes up a mole. Like, that seems like such a random number. But it's not. It's really cool, and it's related to the mass of the proton and the mass of the neutron, right? And you can see these are really, really similar numbers in size. And so when you're adding up the mass of an element, right, you've got the atomic number. So we've been calling them AMU, or atomic mass units. You'll also see them as Daltons. That's the mass of one atom, right, in atomic mass units. That's really, really, really small, right? It's not useful for me, right? Because I can't measure that out on a balance. I can't use it in a lab. I can't get that amount. It's just too tiny. I can't see one atom of anything, right? You'd have to have a supercharging collider thing that shows you an image of one atom, maybe, in, Berkeley. Normal people can't see those. So to make it useful, something I can measure out on a balance, we use Avogadro's number. Avogadro's number is equivalent to the atomic mass units, but in grams, right? So if I weigh out 12.0108 grams of carbon, I have just weighed out 6.02 times 10 to the 23rd atoms of carbon. How cool is that? I know exactly how much I put out on that balance based on its atomic mass, or the molar mass in this case, right? So if I wanted to measure out 6.02 times 10 to the 23rd atoms of magnesium, how much would I weigh out on my scale? Yes, 24.3051 grams of magnesium is 6.02 times 10 to the 23rd atoms of it. How about sulfur? If I want 6.02 times 10 to the 23rd atoms of sulfur, how much do I have to weigh out on my scale? Yes, 32.066. It's like magic, right? Like the periodic table is ultimately cool. So those mass numbers, right, are the equivalent to Avogadro's number, or the mole number, in grams, right, when you're looking at the periodic table. And it's that way for each of the elements. It's a match to its atomic mass units. That's because the elements, as you go across, keep getting bigger. They keep adding protons and neutrons, so the mass of the thing increases for each one. But it increases at this standard ratio, right? You can only add one neutron or one proton at a time, and so you know exactly how big it's going to get. And so it relates to the gram weight. This is super useful for reactions, right? Because reactions are on a 1-to-1 scale. I need to add one part of this to one part of that, and then they come together and make something. I can actually now measure out quantities, not only the mass, but the quantity of a substance, right? I know the number of things that are there, right? So if I need 2 pieces of bread and 1 piece of turkey to make my sandwich, I can count out how much bread I have and how much turkey I have. Same thing with the atoms. If I need 3 carbon atoms to mix with 6 oxygen atoms and whatever, I can now measure those out in those quantities and be able to mix them together based on their mass. Super cool. I know that's a big thing. All right, so 1 mole equals 6.02 times 10 to the 23rd atoms or molecules, and this is equivalent to the compound's molecular mass in grams. Grams is great. I can measure on a scale and get that mass. Right, so if I have the atomic mass of 1 copper atom, that's 63 Daltons, rounded, right, or AMU. And then I have a mass of 1 mole of copper atoms would be 63 grams, would equal 6.02 times 10 to the 23rd atoms of copper that I would have present. And now you're probably like, oh, God, can we move on? That makes me so happy. I love this concept. This is great. All right. So for the periodic table, we can use this for any of the different atoms, right? If we want to know the molar mass of tantalum, it's 180.95 grams equals 6.02 times 10 to the 23rd atoms of it. So that's true for any of these things. You can look at the mass and you can see I have 6.02 times 10 to the 23rd atoms when I have that mass in grams. That is the mole concept. All right, so it's rare that I have just an element. Elements like to form compounds and molecules. And so this is extremely useful when I need to measure out a quantity of a compound as well, right? I just need to add up how much I have present there. Oh, that turned off. All right. So if I have sodium carbonate, right, we looked at these expressions last time and we said that subscript is the number of atoms of that one that we have there. So for each molecule of sodium carbonate, how many atoms of sodium do I have in there? 2, right? Because I have a subscript of 2. So I've got 2 sodiums, right? How many carbons do I have? 1, right? So if it's not given, it's just 1. 1 carbon. And how many oxygen? 3 oxygen. All right, so I can start looking at the molar mass of each of these, right? For the sodium atom, it's 22.990, just off the periodic table. I have 2 of those, so I need to multiply by 2. That gives me 45.98. My carbon is 12.011. I only have 1. That goes straight down. I have 3 oxygens at 15.999. That will give me that number. If I add all those together, 1 mole of my sodium carbonate equals 105.998 grams. So if I measure out that much of the sodium carbonate, how many molecules do I have of it? I have 1 mole, which equals, yes, I have 6.02 times 10 to the 23rd molecules of sodium carbonate, or compounds of sodium carbonate that are present in that mass of it. All right. So the mole concept equals a quantity, and it's related to the gram weight of the atoms that are present in that molecule. This is called the molar mass. All right, so if you're asked to do this in problems, you can calculate the molar mass for any substance as long as you know the formula, right? You can calculate that. All right. Now I think we can calculate that if I can get my screen back. All right, so you need to calculate the molar mass of K2HPO4. So K, there's 2 of those. 39.0983. Uh, 0983. Okay. H is 1.00795. P 30.9737, and O 15.9994.
I just kept 174.1.
All right, so how many Ks do you have? 2. Whoop. Right. How many H's do you have? 1. Phosphorus? 1. And oxygen? 4. Right, and then you need to add all those together.
Do we have to do the whole thing with the significant figures for this?
In the lab, it would depend how far your balance goes out. Right, if it only goes out to the hundredths position, you would need the hundredths position to measure. If it goes out all 4 places, you would want to be as accurate as possible. So it depends. Yeah.
I don't know why I said 170.
You said I got it down. It's like, what?
I don't know why I was saying about that. I was like,
And we have all the responses. Best guesses. And last chance.
pretty good. I was like,
All right, so you should have gotten somewhere around 174.174 grams per mole. Yeah. All right, so we can calculate now how many grams are in a quantity that we need for a reaction. Right, so in this one, we're asking how many grams are in 2.4 moles of K2HPO4. And I gave you the molar mass. Well, you just calculated it. So hopefully it's similar. And this is asking you to show your answer to 3 significant figures and include units. All right, so start with what you have. Right, so what do you have? Yep. 2.4 moles, right, of K2HPO4. Right? We want to get to grams, right? So we would need to use our conversion factor with the grams on top. Grams in 1 mole of our K2HPO4. Right? And our moles will cancel, and our answer should be left in grams. All right, do we have all the responses? And last chance. All right. So you should have gotten 418 grams of K2HPO4. If you just put grams, that's fine. All right. How many molecules are in 418 grams of K2HPO4? All right, what do you need? What do you know about a mole? 1 mole equals the molar mass, right? 1.74.174 grams. And how many molecules is that? All right, so we have 2 of these. So we've got a conversion factor between the molar mass, right, and the number of molecules, right? And we know the gram quantity, right? So we know 418 grams, right? So we need to know number of molecules. So we're going to want molecules on the top, right? So that's a big ugly number. All right, and on the bottom, we have our gram weight. Right. In 1 mole, the grams will cancel, and we should be left with number of molecules. So when you're doing this in your calculator, be sure that you have parentheses around Avogadro's number. So start parentheses 6.02 times 10 to the 23rd, end parentheses. Then you can do your other things.
I think it's 1.45. Because it's 7. Right.
So below 5, round down. Above 5, round up.
It's just 1.44.
You can use a caret. Like so. Caret. Yeah. Give you a hint. Should be up 24.
Wait, how did you put
Yeah.
And then you put parentheses. Yeah.
that happens?
And then you divide it.
Oh yeah, I did it. What?
All right. So hopefully you're able to get this number. 1.44 times 10 to the 24. Oh. So you can use that symbol if you can't superscript. You can use that caret. You could also do it the way your calculator is showing you. So that would be acceptable to write in your box too? Yep. All right, questions on this? Make sure you understand how to enter it on your calculator. I think that's the toughest part of a lot of these questions, is the scientific notation's awful. All right. Okay, so now we're moving on to periodic table trends. So the periodic table, again, very useful for molar mass. You've got atomic number. That is your number of protons, right? That's your Z number. You can determine from your atomic number how many electrons should also be apparent in each atom. The protons and the electrons are equal. You could determine the number of neutrons by subtracting off the mass from the proton number. What else do you have? You have the families of the elements, showing elements that react in similar ways. And we also have atomic size, electronegativity, and ionization energy that we can all predict based on the position of the atoms on the periodic table. So first, let's look at atomic size. So atomic radii moves up as you go down a family column. That makes sense. You've got more protons and electrons that are being housed in the atoms as you go down a family group, right? So if we're looking at our halogen group, we go fluorine to chlorine to bromine to iodine to antimony. And as you're going down, the atoms get bigger. So the radii increases as you go down the family groups, going down a column. The atomic radii, though, goes down as you move across a periodic row. This is counterintuitive because your atoms are still increasing in the number of protons and the number of electrons that they're housing as you're going across a period. Right, so if we look at period 2, we've got lithium, beryllium, boron, carbon, nitrogen, oxygen, and fluorine. And you can see that all of those atoms are increasing in their mass, right, as you're going across, right? Lithium is 6.941 grams per mole, but if you look at fluorine, it's 18.99 grams per mole. That's quite a bit bigger than the lithium as far as the mass goes, right? But the radius, look at the radius of lithium compared to fluorine. The radius of lithium's huge, right, compared to fluorine. Why do you think that is? What do you know about magnets? Like they like to come together. What likes to come together in the magnets? The positive and negative charges. So we not only have the mass inside our atoms, right, but they're charged species. The protons are positively charged and the electrons are negatively charged. So the electrons are inherently attracted to the protons inside the atom. Well, lithium only has 3 protons and 3 electrons. That's not so many, right? So it can only attract those electrons so much to the nucleus of the atom. But fluorine's got 9 protons and 9 electrons. And so it's like, oh, come closer, right? So the radii of the atom gets much smaller the more electrons and the more protons it has, because the protons and the electrons are attracted to each other based on their charge. So remember I gave you that analogy of the baseball field, that the atom's nucleus is the pitcher's mound and the electron cloud is the rest of the stadium? Most of the atom is the electron cloud, so there's a lot of compression that can happen inside the electron cloud to make the radii smaller. So as you're moving down a period, the atoms tend to have smaller radii and get smaller, more dense.
Would that make like a chemical reaction be more, would these atoms on like this side be more reactive because their electrons are less?
They're farther away, yes. And we will talk about that when we talk about the one of the other characteristics of the periodic table, both the electronegativity and the ionization potential. Very good. That is a good thing to be thinking about. All right, so as we go across the period, the radii shrink down. But you can see that as you go down in the periods, that your atoms are still getting bigger, right, as you go down, because this introduces a whole other electron level where the electrons can be. But then at each period, you can see that this trend holds true. That as you go across, they tend to get smaller because in that electron shell, you're having more negative, positive interaction, and they're shrinking that radii. They're holding on to the electrons tighter, essentially, as you go across a period. Good. Okay, so that brings us up to this concept of electronegativity. And this is the measure of the atom's ability to attract a bonding pair of electrons, right? So as you move across the periodic table, atoms want to get to a full state. They want to have their valence shell full. So for most atoms, that's going to mean a number of 8 electrons. Only hydrogen and helium, which would be there if we had the noble gases listed on this as well, right? So hydrogen and helium are full at 2, right? That inner shell can only house 2 electrons, right? So hydrogen wants to look like helium. It wants to get to 2 and be full, or it wants to be completely empty and get rid of its electron completely, right? And then it will be happier state, right? So you can see the electronegativity as you're moving across the periodic table, right? Or the attraction of those electrons increases the closer you get to filling the valence electron shell. So if we're looking again at lithium, I think the I was left off of there, right? So you've got lithium. You can see the electronegativity fairly low. It only has 1 electron, and it's got a big radii, so it's farther away from the nucleus. It's not being held as tightly. But as you go across, right, this one has 2 electrons, 3, 4, 5, 6, 7 electrons. That's almost full, right? So the fluorine is almost full of electrons. It wants that extra one really bad. It's like, I want to be full. I want to have 8. Give me 1 more. I have a lot of electron potential to attract that last electron and fill the valence shell. That's a trend that goes across the periodic table as well. So as you go down in the periods, you can see, like, if you go down in a family, typically the electronegativity goes down because you're introducing more valence shells, right? And they're farther away from that positive charge, so the atom can't hold the electrons as well. The closer they are to the positive charge in the nucleus, the tighter the electrons are held. So fluorine is holding them the tightest, right? Because it has that inner shell, they're right next to the nucleus, and fluorine's like, no, not giving them up, right? And you can see as you go down even that family, as you increase the shells, you get less electronegativity as you go down a family. But the electronegativity typically increases as you go across the periods, and you're filling the valence shell up to 8, right? So the closer you are to 8, the more that atom wants to get to 8 and wants to hold on to the electrons it already has. That's electronegativity. All right, so it increases as you move across a period and towards the right-hand side of the periodic table, and it decreases as you go down a family, right? And again, because you're getting more valence shells. So Linus Pauling is the one who discovered electronegativity or coined its properties. He won the Nobel Prize in chemistry for this work. It's a really important concept when we start thinking about how different atoms or different elements interact with each other and how they chemically bond. So it really was the predecessor for being able to predict how compounds come together.
Are you gonna have these like kind of figures on the exams as well?
Depends. If you need to use electronegativity difference, yes, I would give you a chart like that. So you do not ever have to remember fluorine's electronegativity is 4, right? I won't make you memorize that kind of stuff. That's crazy. That's too much information. Yes. All right. So this gets to ionization energy. Does anybody know what ionization means? Ionization is the ability of an atom to lose an electron, right? So it's the amount of energy that's required to remove the outermost loosely bound electron of the atom. That's our ionization energy. So you can see as you're moving across the periodic table, right, and you're moving across the periods, that it gets increasingly more difficult to remove electrons. you need more energy to pull one off, right? So if I was trying to pull one off of the thing, I would choose something in that first family, way down, not hydrogen. Hydrogen's pretty high, right? Takes a lot of energy for hydrogen. But lithium, sodium down there, I might pick rubidium. Be like, okay, I can pluck that one off. But fluorine, no way. Fluorine, it would take a lot to try to remove an electron off of fluorine. Yeah.
Is it the inverse of electronegativity?
Not the inverse, it's almost the same. Right? So fluorine, right, has really high electronegativity. It has high ionization energy as well. Right? That's the amount of energy it takes to pull one off. I'm going to have to put in a lot more energy to pull an electron off fluorine than I'm going to pull one off of sodium. Yeah. So these are very similar, right? So if you're thinking about the atoms that would rather lose an electron or be much easier, it's going to be the metals, right? They have pretty low ionization potential. Right? The other ones, these nonmetals, much higher ionization potential, much harder to pull electrons off of those. And they're closer to filling their valence shell. All right. So this is a mad summary of characteristics about the periodic table. Right? So as you're going across periods, the ionization energy increases. It's more difficult to pull electrons off. Okay, electron affinity goes up, making it more difficult to pull electrons off the atom. So electron affinity or electronegativity increases. Okay, non-metallic character increases from the bottom of the periodic table up to the top. So fluorine being the most non-metal character of our elements. Metal character increases as you're going down and back across the periodic table. So francium down there being the most metallic. Atomic radius increases going in the left direction or decreases as you go across the periods. And again, that's because you have more positive charge, drawing in the electrons, making those atoms smaller as you go across. So this is increasing size. Right, we can say decreasing over here. Right? Electron affinity also increases as you go up the families. That's again because the atoms are smaller, right? They have more potential to attract the electrons and hold them tighter. So fluorine is the most electronegative atom on the table, right? Ionization energy also follows that because fluorine is the most electronegative. It's holding its electrons the tightest. It will require more energy to pull one off. And then we have atomic radius increasing also as you go down the families and you introduce more space for the electrons to exist. All right, that's all of our characteristics of our periodic table. I think we finished. I don't see any more to do up there. So you can have your 4 minutes back today. And yes, I will see you on Wednesday. We will start chapter 3. Very good.